Heat treatment of steel using carboxymethyl cellulose as a green quenching medium. Effect of concentration on microstructure evolution and wear resistance. By Zainab Aziz Betty and Nadi Aziz Betty. Introduction. The industrial quenching mediums require balancing mechanical performance with safety. Water delivers high mechanical properties but causes severe distortion and cracking due to extreme cooling severity. Oil moderates cooling to reduce distortion but introduces significant fire hazards and environmental toxicity. Polymer as CMC aims to balance stable cooling with absolute environmental sustainability, zero fire hazards, and reduced distortion. Carboxymethyl cellulose stabilizes cooling by suppressing the volatile vapor blanket stages. CMC is defined as a water-soluble, environmentally friendly green quenchant. Aqueous polymer solution provides stable cooling behavior by suppressing the vapor blanket stage that typically occurs in water quenching. This suppression prevents severe thermal shock, effectively reducing quenching distortion and cracking while completely avoiding toxic fumes. Novelty. The metallurgical breakthrough relies on ultra-low 0.1% weight polymer concentrations. The prior focus was on analyzing psychochemical properties such as wettability, cooling efficiency, while the new focus on the direct metallurgical and tribological impact of ultra-low concentrations. Experimental approach. The experimental thermal cycle includes austenitizing, quenching in water, and other samples in CMC solution. The third phase was tempering. Validating performance requires rigorous standard testing methodologies, such as tensile testing, micro-hardness, abrasive wear, grain size. Results. Gradual variations in cooling severity systematically govern ferrite grain size, increasing the CMC concentration, gradually decreasing the cooling severity of the medium. This systematic reduction in cooling speed directly influences the evolution and scaling of the ferrite grain size, giving manufacturers a controllable variable for microstructural engineering. Tensile strength. As shown in figure, sample B and D exhibited the best strength-ductility balance, while sample C showed the highest ductility. The results confirm the strength-ductility trade-off, with water quenching maximizing strength and polymer quenching providing a more balanced mechanical performance. Hardness and grain size, as shown in table, compared with the as received sample and water quench sample. Samples B, C, and D exhibited lower hardness and generally coarser grain structure. These results indicate that the use of CMC as a quenching medium influenced both grain size evolution and hardness response after tempering. Wear rate. As shown in figure, the overall trend refers to the fact that quenching in the CMC solutions improved the wear performance compared to the as received sample, denoted by AR. SEM of the worn surface. As shown in the two figures, SEM images of the worn surfaces of the as received and sample B with 0.1% weight CMC, with the adhesive wear behavior being dominant. A large amount of plastic deformation, layer fragmentation, and the appearance of debris were observed in sample AR, indicating repeated adhesion and fragmentation processes. Sample B showed the smoother surface, less layer fragmentation areas, and fewer grooves. which were a sign of its good wear resistance. Conclusion: the 0.1% CMC concentration achieves the optimal industrial sweet spot. Water spikes high in hardness but fails in distortion and wear resistance. 0.1% CMC maximizes the overall area of optimal performance, providing robust mechanical properties, superior tribological performance, and entirely eliminating chemical hazards. Finally, green quenchants solve historical flaws on the manufacturing floor, including production efficiency, operational safety, and true sustainability. Thank you.